In this next section, we'll be going through content addressable memories, also known as CAMs, read-only memories, known as ROMs, and programmable logic arrays, known as PLAs. CAMs are kind of an extension of ordinary memory, in other words, the SRAMs that we spent a lot of time on. In terms of reading and writing to the memory is the same as you would do for an SRAM. And so the bit structure and the reads and writes are all almost identical to an SRAM and can be identical to an SRAM, but they also include some additional transistors that allow you to do a match. And so they have an additional input, which is a data key that can be read into the CAM or sent into the CAM. And that data key will be compared to every word in the CAM. And if one of those words matches that data key, you will get a match output that will be high at the end of the compare. So we'll go through the details of how that works in the next couple of slides. On this slide, you can see the structure of a 10 transistor or 10T CAM cell. And we have both the schematic and layout demonstrated here. And you can see the schematic has the exact same structure initially as an SRAM cell, where you have a back-to-back inverter, and then you have two NMOS devices that attach to either sides of the back-to-back inverter and connect it between the bit cell and the bit line and bit bar line. Now, in addition to that, you have 4 additional transistors, and these transistors you have 2 NMOS in series that connect up to the match line, and one of them is, so on the left hand side you can see 2 NMOS in series that one of the bottom one is connected to your bit line, the top one has the gate connected to the cell bar part of the memory, so the inverted memory bit value, and the drain is connected to the match line. And the other NMOS stack, 2 NMOS in series, is connected between ground, and the gate connection of the lower NMOS is connected to the bit bar bit line coming down, and the next NMOS in series with it is connected up to the internal bit cell non-inverted value, and then its output is also connected to the match line. And in effect, what winds up happening is if the key is driven onto bit and the key bar is driven onto bit bar. And so the key value is on the bit line in effect. And if the match line is initially precharged, so this is another case of kind of domino logic, so you precharge the match line. If the bit line matches the value in the cell, then cell bar, it won't match the value of cell bar. And also if bit bar, which is the inverted value of the key, and if the inverted value of the key matches the value in, or if the inverted value of the key matches the inverted value of the cell value, it would match cell bar, but it would not match cell. So if the bit value matches the cell value, you will not have a NMOS stack in series that is both turned on. One of them will be turned on, the other will be turned off, if you match exactly what the cell value is. So only if you match the cell value, you don't discharge the match line. And if you don't match the cell value, then you'll discharge the match line. So that's kind of how the match line works, is you only discharge the match line if you don't have your key matching the cell value. So here we go into a little bit more detail on the actual cam cell and full row and column operation. So the read and write into the cam operate just like any ordinary SRAM. But when you do your matching, what you wind up doing is you leave the word line low. You don't assert the word line at all. You pre-charge all of the match lines, as I mentioned in the previous foil, and you place your key value on all of the bit lines after you've finished pre-charging the match lines. And at this point, once the key values are on the bit lines, the match lines will wind up, that's effectively the way the match lines evaluate. When you're pre-charging the match lines, you actually want both bit and bit bar, the bit line drivers, to be low. You know, it's kind of like a normal domino circuit where the inputs need to be low while you're doing your pre-charge. And once you finish pre-charge, then you can raise the value of either bit or bit bar depending on the key value in order to potentially have the match lines evaluate. Now, if, like I said on the previous slide, if the value of the key matches a given bit, whether it's in a given word or not, you know, for each given word, you check, you know, you get compared for each word. All the bits on a given word will match, you know, a given match line. So in this case, we have 4 different words shown. Those are the 4 rows. Each row has all of its bits connected to the match line. If any one bit mismatches, it will discharge that particular match line. If all of the bits match the key, it won't discharge the match line. So in effect, as long as all of your entries in the array are unique entries, such that your key is only going to match one entry, in effect that means that all the match lines will discharge except for one, the one that matches. So you wind up pre-charging all match lines and you discharge all but one as long as you match a key value. So in effect, that's the way it works. And so the match line will stay high if the match line will stay high as long as a key matches all the bits of that particular entry. And if that stays high, then the miss line will wind up going low. If you see in the circuit there's a miss line that's effectively NORing all of the match lines together. But if all of the match lines go low, then the miss line is going to go high. So the next memory array that we're going to go through is read-only memories. And the key thing to know about read-only memories is they're non-volatile, which means they retain the value of the memory value even when power is removed from the system. And there's a couple different ways that we can get read-only memories. One way is using mask programmed ROMs, where we only need one transistor per bit, and we use a photolithography mask up front to program it, and in effect attach a transistor to a given intersection or a given line, depending on how we want to program it up front before we even manufacture it. And so if there's a transistor programmed there and attached to the line that determines whether we get a 0 or 1. So if it's there or if it's not, we either get a 0 or a 1. And again, this is something that's determined before we actually fabricate the chip itself. So here you can see an example for a ROM. The example is a 4-word, so we have 4 rows with 6 bits, so 6 columns, and so it's a 4x6 array, and for each bit that we want to have a value of 1 on, we have a mask that we basically pattern a transistor that's attached, whose gate is attached to the word line for that particular word, and whose source is connected to ground and drain is connected to the bit line for that particular bit, the column bit. And so if we assert, let's say, the topmost word, the word line for the topmost, you can see there's 3 transistors in that word. One transistor is connected between ground and bit 4, so we have bits 0 through 5. So bit 4, there's another transistor connected to bit 2 and a transistor connected to bit 1. And so the word 0 at the top there would have 3 of those bits would get pulled low, and then they go through an inverter and the value of Y comes out, so they would be high at the output. So wherever there's a transistor, the bit value that comes out, you get a 1 value out. And so you can see word 0 is a 0, 1, 0, 1, 0, 1. The next word has also 3 transistors, but the first one is no transistor, and then 4 and 3 are both going to be 1s because there's a transistor there, and bit 0 is going to be a 1. So that's going to be 0, 1, 1, 0, 0, 1, and etc. You can follow the next 2 rows and go through what those should be, compare it to the values in the upper right, and make sure you understand that. So you can either draw it out as the schematic has in the lower left, or what's commonly used is something that is like the dot diagram on the lower right, where the dots indicate where a transistor is and effectively where you're gonna get a value of 1 out of the ROM. So the horizontal lines are your word lines and your vertical lines are your bit lines. So this kind of shows you how you'll get those values out of the ROM. Like I said in the previous foil, this type of ROM is programmed before you even start manufacturing masks. It's not something that you can program after you fabricate the actual IC chip. Once you have the IC chip, the connections of the transistors and their placement are all fixed by the fact that you decided to place them there in the initial design. So this is not a programmable ROM, this is just a read-only memory, pure read-only. Here we can see an example of the layout for the ROM that we showed in the previous slide, where we have a 4x6 array. In this case, in effect, our word lines are just lines of polysilicon that are overlapping active areas, and the bit lines are kind of just one layer of metal that are making connections to the transistors where they appear. And so you can see it's much, much more dense than an SRAM, because all we need is a single transistor in order to effectively carry a bit of value instead of a 6T cell. And so it's much easier in some sense from a difficulty of connections and figuring out what the logic is. But again, it's not programmable. It's a very dense way to store memory. You can see here the unit cell of one transistor is 12 by 8 lambda, so it's about 1/10 the size of an SRAM cell. So you can get a lot of memory, but again, it's read-only. You can't change the value of this memory once it's created. Here we show an example of doing the row decoders for the ROM that we've been talking about, and the layout that you can do for those. Keep in mind the row decoders must be pitch matched to the ROM that we created, which means the ROM, since it only had a single track per word, the row decoders also need to be just a single track per word. So again, very dense construction of these, but much more efficient in terms of area. So, this is something that is very small area, pretty energy efficient, but again, using a ROM is something that you can't program it, or you program it once up front when you're creating it. Once the chip is created, it's again read-only. You can't change the value, so if there's a mistake or some problem, you have to go back and actually construct new chips with new values. And finally, here you can see the complete ROM layout, including the decoder, some of the logic going into the decoder, and then kind of on the middle, on the right hand side, is the actual ROM array, and then reading out to the bottom, we have the inverters that take the bit values coming out and create our final output values coming out at the bottom. And so again, this can be, you can see in this particular case, a lot of the control circuitry around this array, partly because it's such a small array, the control circuitry actually takes up more area than the array itself, because the array is so dense, only needs one transistor per array, or one metal track per in both X and Y for each row and column. You need one metal track in effect in each direction. So can be very small area structure, and potentially your decoder and other logic around the array might wind up taking up more area than the array, depending on the size of your array.